Hey guys, thanks for being here for the last talk of Black Hat 2015, and especially also competing with DEF CON, which is running in parallel. Now we got a little challenge here. The slides you see here, I could not get them to fit on the screen. You've seen us fighting with it. So the challenge is you got to fill in the blanks. All right, so we're going to work with that way. Okay. How many of you are computer security officers or people who work in security in the organizations? Wow, oh, that's pretty good. Of course, you're in Black Hat. You got to be there. All right, how many of you deal with malware as malicious program? That's pretty cool. And so you got terabytes of malware. Anyone with a terabyte of malware? Yeah, there you go, terabytes. Gigabytes, lots of them. I got in my lab too. What do you do with them? You got terabytes of malware, so you sell to each other, right? You say, hey, here's my terabyte. Let me pass it on to you. And people go about collecting malware. And what we want to do in this talk is tell you how we can convert this terabytes of malware into source of intelligence. That's the focus of the thing, is how do I convert it into something useful rather than something that you can say, oh, I got terabytes of malware, I'm so proud of it, but don't touch it. Okay? I want to change that. Let me introduce myself. I'm Arun Lakhotia, and I'm professor in the University of Louisiana at Lafayette, and I have with me my colleague, Vivek. Because we have lost time, I'm going to rush through this part. Let me see. So here's the thing, Cybersecurity Disconnect, the last part on the top. So have you heard of this event that happened in the White House when someone had a drone that landed inside the White House lawn? You heard of that, anyone? Nah? Okay. All right. Okay. So some have heard. So what happens when you have these kind of physical security incidents or violations? Typically what happens is you get a whole bunch of, in this case, Secret Service comes zooming in onto the people, whoever has done whatever, and they go through the complete history of the person to find out what was it about. Now, even if your own home, let's say you went home and you found a window to be broken, you are likely to call 911, find out what's going on, who is after me, even if the perpetrator has not gone in because your dog was barking. Right? So you had a defense. However, when the incident happens, you're not just happy to say, okay, let it go. It's okay. No one took anything out of my house. Okay? There's a disconnect here. When you have cybersecurity incidents, and the incident is just an attempt, someone trying to get in, you kept them out, and you say, okay, man, that's good. I kept them out. I don't need to worry about it. It's only when someone actually steals a whole bunch of credit card information and things are going all over the place is when you start reacting to it. And what we want to do is change that. And it connects very well to what Jeff Moss said in his keynote. Essentially, he said, when you're under cyber attack, why do you not employ every resource at your disposal? In the context of his conversation, he was also bringing in law enforcement. Why don't we call 911 in a sense? Why don't we go pursue the offender? Now, if you're going to call 911 in this sort of situation, you need intelligence. It's not just enough to say, okay, I got attacked and so on. At some point, you got to have to extract information so that you can somehow pursue the perpetrator. And what we want to do is convert the malware into intelligence. Now, the basis that we have here, the missing part on the top, is we're going to talk about extracting intelligence based on the economics of developing malware. So you look at the model of developing malware. As a starting point, we know malware is software. And we know writing software is expensive. Rather, writing good software is expensive. And we're talking about malware. It's a program that if it crashes, the user is not going to call back and ask you, hey, help, it's not working. You got to have the program that works in a remote machine and hopefully doesn't crash the machine, because if it crashes the machine, all bets are off. You're not going to get anything out of it. So you have a program that's going to be intense in terms of complexity. And you're generating those programs, and have you heard the numbers? You get like 200,000 malware a day nowadays, something like that number. It used to be 200,000 a year. They've been doubling every year, so most likely next year when you're here, it'll be 500,000 a year, a day. That number is big. That's an extremely big number. It's a complex software. There can't be that many programmers writing programs, malware every day. They're throwing 500,000 malware every day. They got to be developed in some other ways. So you have complex software, 500,000 of them every day, throwing at you a new software in some sense. So the economics of developing malware essentially goes to this effect. You got to use some automation. You got to use some way to create lots and lots of variations. And that's typically what happens. You have this packing, polymorphism technology, where you you take a program and you sort of wrap it up in some kind of a form, let's say envelope, that looks very different in every instance. That's one kind of a morphism obfuscation you do. You can also obfuscate the code itself. You transform the code, what's classically called as metamorphism or polymorphism. And of course, you're also using a variety of different libraries. So typically, when you're developing malware, you're going to buy, borrow, steal somehow the actual code. You're going to put it together. It's a complex code. And then you're going to transform the code, and you throw it all over the place. This is a classic way. So if you're going to have a zero-day attack, let's say you've got an exploit, and you want to penetrate an environment, besides the mechanism to penetrate, to infiltrate the environment, you also need the code that once enters the environment is going to do something useful. And it's extremely likely the code is not written in 0 day. The code is written a very long time, and you're going to reuse that code. So what we're doing is, we want to say, can I extract this intelligence, information out of the malware so I can make connections? I know the code has been written and rewritten and borrowed and stolen and whatnot to create something, and then it's been transformed after the fact. So we're going to use this model. We are transforming the code after the fact, and we are reusing code. And we're going to try to see whether we can essentially find a way to connect malware based on their code. So what are we going to get out of the intelligence? If I have ways to relate malware, not just say it's bad. We want to say, okay, it's using this particular type of library for some attack. Maybe it's using this encryption library. It's using this code for backdoor. It's using a particular kind of code for keylogging. It's using a variety of code. All of it has to be professional, production quality code to work. It's borrowing that code. Now, if I can make connection between malware, I could potentially say, well, these two things, there are two actors, one that's attacking a bank somewhere and one that's attacking an NGO somewhere. Maybe they are connected. There's a relationship between them. Okay? We could find connections between maybe something that's attacking that's been received at your unit in India, maybe, or China, or some other part of the world. You could find connections between the code and say, hey, looks like someone is targeting us. And the intent is not just to have terabytes of malware that you're sitting on, but to find connections so that the 200,000 or so malware samples you have coming at your door every day, you can partition it in some ways so that you can say, it looks like this little piece of code, they're coming after my sales department, or they're trying to hit the sales here and a marketing team there. Maybe there's a connection. Okay? And that's the intent. Well, what's the evidence that we can find connections? And it turns out if you look at it, and here's one particular piece, one article which says that Stuxnet, Duku is in this case the precursor to the next Stuxnet. So here, essentially what this article says is you got the code, Duku shared code from Stuxnet. And then you have the case of Duku's code being used in some other place. You find articles from Kaspersky. They're pretty good in that. They have a lot of articles from Kaspersky. They go deep into the code and find connections between what might be considered families of malware. So there is enough empirical evidence to show that the connection exists, that it's in the code, that people share code. What we want to do is, can we do it in scale? So while you have Kaspersky and Symantec, they're researchers sitting and actually extracting information from code, we want to do it automatically, and we want to do it on scale. So what we want to talk about today, essentially, is a mechanism to extract intelligence from malware on a large scale. So, see? So let me see what we're trying to achieve. In the breadth, we are developing what might be called a Google for malware. So think of it, if you have done Google image search. If you've done image search, you take an image, upload it in Google, and it's going to search, take the image as a query, and find other similar images. So imagine the same thing here. You take a malware, you upload it in a site, and it doesn't just tell you, hey, yeah, Symantec says this is a bad thing. It says, okay, and it's also similar to all of these other things we have. And of course, not just the similarity, you want to say, okay, what is similar? And can it potentially give you more information? So that's sort of our requirement. We want to develop some notion of ways to match a given malware with a very large collection, your terabyte collection of malware. So the challenge, let me outline the challenge involved. The starting point is some notion of malware, which is some little piece of code, scary looking stuff. And typically it's obfuscated. So you want to have ways to de-obfuscate the malware. Then the next step is we're going to map this notion of malware into what's classically called as a document. And a document is not a word document. Document is just a phrase used in information retrieval to represent something. The whole, some of the ideas come from as in a text document, but we'll really not create document. We'll create a notion of words, a notion of sequencing of words, and so on. So we have a mapping to document. The next part is, of course, creating indexes. Indexes so that you can search the collection very fast. So that's the four-part problems. So I'm going to go through all of the pieces, and I'll give you a high-level view at each part. I'm not going to give you necessarily all the gory technical detail, but give you the big picture at each part. So one of the key innovations, some of the key innovations we bring is we're going to use VM introspection, and we're going to use it in the cloud. So essentially what it means is cloud is typically, you have a machine, you break it up into a whole lot of virtual machines, and on the top of the virtual machine, we're going to run other virtual machines that will contain Windows, and then we're going to watch the virtual machine running inside the virtual machine to figure out what the program inside it's doing. And we can do it in scale, as in, so that enables us to do it in scale, which means we can now potentially analyze malware on something like Amazon cloud if they permit you. Amazon doesn't like you to run malware in the cloud, but if they did, you could potentially do it there. Another key innovation we bring is what we call as a semantic fingerprint. So on the part, the semantic fingerprint is essentially, if you look at bytes, and I told you the malware economics, you transform code. You're going to try to obfuscate the code. So obfuscations mean somehow you're transforming the sequence of bits. So we don't want to have fingerprint that's based entirely on just the bits in the code. We want to have fingerprints that's based on what the bits are trying to do. And that's what we call as semantics, as in what is it actually trying to achieve. And the achieve here is in the actual code. So there are two levels of achieving. Achieving is you look at the behavior, as in what's called as behavior in the sense of FireEye, behavior of what the malware is trying to do by talking to the Windows OS. Here we're talking about semantics of the code itself, as in the program that malware uses to perform something. So we want to extract the semantics, and we want to use the semantics as as for fingerprint. And remember the malware economics. People are sharing code. People are transforming code. So if I can have a way to untransform code and then find a way to match shared code, then I have a way to create fingerprints based on code. Now, what happens, of course, I'm going to skip this because we're going to talk about it a little bit more. So the first challenge is code obfuscation. And there are two parts to code obfuscation. One is removing an outer shell, which is called packing. Remove the outer shell. And the second is even the inner shell, the code itself may be similar but different in bits. And the second part is to map similar code to similar form. So in the outer shell, what we do is we have a VM. We have a method to unpack malware inside VM. The part that is so there's a whole lot of people who have done unpacking before, and so we have some innovative methods of unpacking, but given the time constraints, I'm not going to go into the details of that. I'm going to focus on something that is more exciting that no one else has been doing, which is normalizing code. So what is missing on the top, the fill in the blank, their part is the code normalization. So how do you normalize code? So the normalized code means something like this. The problem is something to this effect. You have this code segment. And so when you transform code, you could potentially convert it into these various different code segments. What happens is all of these pieces of code that you're seeing, they all perform the same task, exactly the same thing. Okay? But as you see, the code is different. What we want to do is map this code to the same form so we can have just one representation for all of these various pieces of code. And the way we achieve is by mapping code to semantics. And what does that mean? So this is a piece of code in this case. And semantics is an algebraic expression. Just like linear algebra, you have a simultaneous equation. So it's a collection of simultaneous equations that describe what the piece of code is attempting to do. So in your algebra, if you remember now, you want to say, oh no, don't talk about algebra, it's been so far away, don't want to talk about it. But the key thing in algebra is you can simplify expressions. When you have a collection of simultaneous equations, you simplify the expression, bring it to the simplest form, and that is essentially what we do. We take the original program, we map it into semantics, and then we simplify. Simplification requires the same kind of properties that you use in algebra. You have a distributive property, commutative property, associative property. We use all of those properties to simplify. Now, it turns out there's nothing magic in it, nothing new. It's used in compilers all the time. When your compiler tries to optimize your code, it uses all of these tricks. All we are doing is bring the same tricks to understanding, extracting meaning from code. All right? So that's the first part. The second, so this is, remember, obfuscation. We can unpack and we map it to code. So we have, in a sense, removed all these code variations and mapped it to a sequence of simultaneous equations. The next part is to map it to document. We want to create document. So in document is where the challenge comes in. We want to create a representation so we can search on a very large scale. So we don't want to compare two documents at a time. We don't want to pick a document and then compare, is this the same as that? We don't want to do comparison pairwise. So if you have a terabyte of malware, you don't want to be taking one sample and matching against each of them. We want to create indexes so that you can take a document, break it into pieces, hash pieces, look up similar things, and bring them out. The keyword there is hash. I want to be able to create hashes such that when I map this semantics to a hash, if two pieces of code have similar semantics, similar in some notion of programmer may say same, it will have the same hash. That's the key second part. And once you can hash it, it addresses a whole bunch of things. You can use your distributed databases like Mongo to represent a document on a distributed architecture, and that gives you the scale that you need to search a very large collection. So what's the trick? We want to represent binaries, and so the classic method of representing binaries is taking a sequence of bits and converting it into a variety. So let me back up. There's a variety of ways to convert bits into document. What we are using is using semantics. What some of the other people have used is taking the actual bits to represent document. When you use actual bits, you get a lot of power. It's pretty fast. However, it's not good in the sense that if very similar documents may have different bits. So we want to match semantics. Our strategy is we take a binary, map it into disassembly, convert, create a control flow graph, and this is where it comes. We create what's called as, on the bottom you see the two parts is semantics and something we call as juice. Juice is very similar to orange juice. You take orange, you squeeze the orange, what you get is the essence of the orange, the juice, and you leave away the fluff. That is what we want to do here, where we take a binary, squeeze it, and extract what we're calling as the semantic juice. So I'm going to give you an overview of what is semantic juice. And so when we're talking about words, semantics to word, the challenge is how do I make sure that when I have two things that are very similar, they end up having the same word. So when I hash, it's exactly the same. And when I say hash, the hashing is applied on string. Remember that when you do Python hash, you take a string and you hash. So I'm going to actually create string as a sequence of characters. And when I hash it, they should be the same. So you have a program with different code, map it into a semantics, map it to juice, create a hash, and I'm going to search. So the big challenge that we have, and I'm going to give you a big picture of the challenge is like this. So you have this sequence of simultaneous equations. You can reorder the equations and they still stay the same. You can reorder the terms in the equations because there's associativity and commutativity rules, and you can reorder terms, you can reorder equations. They are still the same equations. What I want to do is be able to impose an order so that given two set of equations that are equivalent, I have the same order. Okay? So the way we do it is we introduce some ordering rule. We introduce our own ordering rule. So string ordering. So you can use your dictionary order. And by and large, if you impose a dictionary order and you introduce a little bit of tricks involved for dealing with commutative and associative properties, a little bit of tricks, you can essentially get, for a very large collection, not always, but a very large collections, you can get same semantics, same strings, same identical sequence of equations for the same code. But for a little catch. Like in your algebra, you have the variable x, and you change it to the variable y. It's still the same equation. If you are consistently change the variables. And the catch is, how do I deal with these variables? How do I take two equations that are equivalent, but the only thing they differ on is the variables, and ensure that they are identical? Okay? That's a little trick that's involved. So here, what we do is, we take the variables and we use something used in, we use a little trick used in logic programming. So I'm going to skip some of these to give you this part here. We use a trick used in logic programming. You heard of Prolog, anyone? No Prolog? Yeah, there's a Prolog guy. So in logic programming, you convert essentially what is called as the variable x, let x into what is called as a logic variable. Logic variable is like a quantifier. There exists x, or for all x, you create a quantifier. So you replace all the symbolic variables, x, like an EAX, a register, you replace it with a logic variable. And then you take all the logic variables, and there's a way in Prolog to what's called as a unify terms. Unifying means given two terms, you can unify them and say that they're equal if all they differ is in the logic variables. That's the key thing. Prolog already gives me the power. Given two set of equations, if the only thing they differ in is the logic variables, so the variable names, I can abstract it, and then I use Prolog unification. If I unify, if two sequence of equations unify, they are equivalent. It's as simple as that. Okay? So we abstract it up, then we use Prolog model of unification. So now essentially what happens is, while you have a logic variable, you still need to give it a name. There's still a little bit of tricks involved in making sure that two different equations with different symbols in the beginning can be mapped to the exactly identical sequence of strings by replacing all the symbols by logic variables and then giving them a different name. So there's a little bit of tricks involved there. But so I'm going to just leave you with that. It's doable, and that's essentially what we do. Okay. So I'm going to skip this. My guess is I'm running out of time. He's looking. Okay? Yeah. Okay. So anyone wants to learn more about it? About computing juice? I have a slide that I skipped. Let me give you the little thing here. This is what's happening. It summarizes a lot. So you see on the top part is code. So you have a binary converted to disassembly. And what I do in the second box is the semantics. And when I'm computing the semantics, I actually do what's called as a symbolic interpretation. I interpret the code symbolically. And symbolic interpretation is nothing different from algebraic simplification. So I simplify it. And when I'm doing the simplification, I track everything I do. I keep track of the steps performed. Once I've simplified it, I go to the next step, where I replace all the variables, EDX, EAX, EBX, those are like your algebraic equations variable. I replace them by logic variables, which is the uppercase letters. So I have this. And then when I keep track of what transformations I applied, that's an extremely valuable part. If I know the method I used to simplify, when I find two different pieces of code, and if I can relate them by the same steps, simplification steps, it tells me that they are using the same obfuscation steps. Right? Makes sense? So that's roughly what we do here. Okay. So the next part is, how do you create indexes? And indexes means you're going to want to be able to quickly find that little needle. In this case, there's a needle. At the end of the red thing, there's a needle in the haystack, and there's no red string that you can find. Okay, you just need to find needle in the haystack. All right, so that's the intent, and we want to find it fast. It's a relatively simple problem. Once you have computed this thing, what I call as juice, and once I have mapped it in a form that the string, the actual string, you can compare strings of two blocks of code and say if the strings are same, they are exactly the same, or they are very similar. If once you can achieve that, then life is extremely simple. All you have to do is go back to these people who are already doing data mining. People like Google, who know how to find search through large collection of data. So that's really what. All we need to do is compute hashes. And so here what we do is something called, what's the blank part, this cutoff is, we create what is called as a min hash. So let me visualize the problem for you. So you have two documents, like I said, documents. And the document is a collection of juice. So you have two collection of documents, and then you compare the document and say, hey, do they have a lot of similar juice? Right? That's essentially what we're doing. So you got documents, you got another document, so you're trying to match. You don't want to go about doing pairwise matches. You don't want to pick one document and say, okay, these has these kind of words in it, and there's another document, these words, and you match them on words. That's very, very expensive. Instead, what you do is you create what's called as a hash. A min hash essentially says that, hey, let's just pick one attribute of the document. So one attribute, and here in example, an attribute, if my document was people and representation of information about people, I might say, let's just pick hair. If two documents match on the hair, there's a very good chance they're very similar. So you randomly pick some, what's called as a feature. You randomly pick a few features, and if things match on this feature, it gives you some insight into that the similarity, the probability that the two documents are same. So you're not doing exact match, you're doing a probabilistic match. You say, well, let me pick 30 features and just match on 30 features. So instead of having 10,000 features, you're randomly picking some 30, 40, some number of features. And the number of features you pick gives you a way to tune your the quality of match with respect to the cost. So that's roughly what happens. We identify features, we identify them randomly. It's called a random function. We apply the same random function on a set of collection of documents. And now by picking a collection, we have to now choose the number of random functions to apply. And what we find is all we have to do is apply 11 random functions. So we have 11 random functions that we apply to pick up what is called a similarity between procedures, code units, the functions. So all I want to do is first find similar functions. Once I find similar functions, then I can say use that to find similar binaries. So we do min hash to find similar function, and then we use that to find similar binaries. The key is we want to have a notion of search at various level of granularity. So you want to find, hey, I have this function. Is this available? Is this used in this terabyte of data I have? Or I have a collection of functions. Can you find me other binaries that use it? So we don't want to be limited to just a notion of a full image search. I want to be able to do some notion of a partial image search. Okay? So the model is you create document, you compute hashes, and in this case we compute what's called as a min hash. And min hash gives you a way to search through a large collection relatively fast, but probabilistically speaking, and with certain level of probabilistic guarantees. That's it. Now put it all together as an architecture, our system that we have. The steps of moving binary to hash roughly involve this. You have to take the binary, you unpack it, you disassemble it, and then you break it into procedures, and now I compute the semantic hash. Once I extract the semantic hash, I compute min hashes to create indexes for procedures, and then I use min hashes to find similar binaries and do whatever else. And this is we have it implemented in a web service called Virus Battle. If you go to virusbattle.com, you'll find the web service where you can upload the malware, and it will go through the whole process right online, and then you can query and search for similar binary. It's a pipeline architecture. It's currently using Pyro as a mechanism to schedule our individual components. We can distribute the components in any number of machines and stuff. The key part is it's not limited to working as a one unit on a single computer. We can distribute it. Now I'm going to have transfer to Vivek. He's going to give you some insights in some of the results we have received. Okay.
Hi. So, how many of you actually understood everything that he talked about? Okay. Well, so the good news is, well, he's a professor, and well, this is not an assignment. It's something we've already done, and you can now use it. It's available online. And if you're a company, hopefully you can pay us to use it online. And so I'm going to show you now that he's been talking about, we've been building the system. How do we actually go about and use it? Everybody talks about intelligence, but what exactly are those intelligent results, and how can we actually apply those? So to do that, we did a case study with FBI, and they were kind enough to provide us with some malware samples. It's distributed across 14 malware families, about 2,500 PE executable files. That's what the system currently takes as input. And this is a malware that's been collected over a year. And we put it through the system, and first it went for unpacking. And well, what this graph essentially shows is that this is the distribution of how the malware was distributed across the malware families. As you can see, it's not very evenly distributed. But the blue bars show the original files that were input into the system, and the orange bar shows how many of those files we were actually able to unpack. And when we say unpack, what we're actually saying is that we let it execute in a VM, and we found that the sample wrote some new code into the memory, and we were able to extract all of that new code and put it all into form of a PE file and send it through the system for generating the semantics and the hashes. And what this table summarizes is that, well, we use 3 kinds of heuristic to detect, okay, when the unpacking has been finished and it's time to actually extract the contents from memory. And So most of them go through an algorithm called hump and dump, which basically relies on recursive execution of the packers. But we cannot go more into details right now. But what it essentially shows is that we were able to use binary similarity to say, oh, the new generated unpacked binary was not so similar to the initial original packed binary, which means a lot of new code was generated. And as you can see, almost 88% of all the files were successfully unpacked. We only had roughly 12% failure cases, which is pretty good considering this is a generic unpacker. It's a fully automated system. Now, how do we use those information that we got as intelligence? So this is the first example of true intelligence. What I have over here are a graph that essentially shows how the same malware was being packed using different packers and then distributed out in the random. All of those red icons represent the original malware files that we had. Those files were what we input into the system. The yellow open box type icons are the unpacked files, and the skull and the skulls essentially represent the CNC IPs from where they were extracted, or what they were communicating with. And so we look at that. There are several of those red icons that essentially go down to one unpacked binary. And all of these are like SHA-1 matching unpacked binary. So they were essentially the same unpacked code, but they were packed using different packers and hence the different binaries. So that is one true intelligence that we actually get out of the system. The second is, okay, now what Dr. Lakhotia did through his semantic hashing was that he was able to collapse a lot of procedures and say, oh, these procedures are essentially the same procedures, okay? So if they are same procedures, only they've been obfuscated differently, which is why they look different, that means that any knowledge that you have about any one of those procedures can be propagated to all of the other procedures that are exactly the same. So we went to IDA and we put in all of the procedures and we said, okay, can you tell us about any of the procedures that you have over here? And well, all of these, the blue parts are the percentage of procedures that IDA identified as being library procedures. Once you know that a procedure is actually a library procedure and you know which library procedure has been identified by IDA, then you know essentially what the procedure does. Once you know what the procedure does, you really don't need to reverse engineer it because you have all the information already, right? But as you can see, it's not too many blue percentage over here or library procedures over here. But we were able to use semantic hashes and so propagate that knowledge, okay? That if two procedures have the same semantics, essentially they do the same thing. So it doesn't matter if IDA is not able to identify that these are the same procedures. We know they are the same procedures, so we don't need to reverse engineer them. And so we propagate that knowledge, and this is what we get. Almost half of the procedures now don't need to be reverse engineered. That's the beauty of semantic hashes. And this is now new intelligence and new knowledge, new inferences that we've got that we were not able to get previously. Okay? Now the impact of this. So when we had those 2,500 binaries and we broke them up into procedures, what we got was this red graph. As you go from left to right, the number of binaries are increasing. And on the y-axis, we have the log to the base 10 of the number of procedures that we got. So the number of procedures kept on increasing, okay? I'm going to show you how many. We go to approximately 1.7 million procedures in just 2,400 binaries. Now that's a lot of procedures. So we said, okay, what if I am only looking at the code blocks and I just do a cryptographic hash of the code blocks, no other analysis, just the cryptographic code hash. What I get then is the green line. And that's only about 100,000 procedures. So this validates the initial assumption that Dr. Lakhotia had, that malware is not being rewritten every time. You use a lot of code that was already used. You know that code is already, you have some code, you have time tested it, and you can use it again. And so you keep using it again every time you create a new malware. You borrow some modules, or you borrow some features, you borrow some procedures. And so from 1.7 million, we got down to 100,000. But then these 100,000 are still code, obfuscated code, and not truly unique procedures. When we go look at the juice of these procedures, we go to this blue line, and we get only about 32,000 unique procedures. So we've gone down from 1.7 million to 32,000 procedures. Just imagine the cost of reverse engineering that you've saved right now. It's order of magnitudes. And now if you look at these graph lines, you see that the distance between these graph lines is increasing as you move towards the right-hand side, as you move towards positive x-axis. But on the y-axis, this is not a linear graph. This is the log to the base 10, which means every time the distance increases by a unit of 1, you've actually decreased your cost by an order of magnitude. You've gone 1 decimal place left. And this shows the percentage of library procedures as identified. So the percentage of library procedures obviously is increasing, as we saw in the previous graph. Now, another impact of this intelligence is that we were able to connect malware families that we previously thought were very different or disparate and not known. Now, again, the red icons are all original malware packed binaries, and the open box structures are unpacked binaries. But this graph has 4 malware families. Okay, this one yellow colored smoke loader. Black is, I think, Dark Comet, purple is Pony Loader, and green is Aldebot malware families. And if you see, they are all clustering. Each family forms its own cluster, except for somewhere in the middle, you have a cluster where some packed binaries are coming in from each of the malware family. But when you look at their corresponding unpacked binaries, the unpacked binaries go back into the family's cluster. So what this shows us is that sometime all of these malware families were sharing the same packer. We went back into their own, all of the unpacked binaries, they went back to their own cluster, which means the underlying malware code was still different. They all probably created their own separate malware. The families are not the same. But for some of their packed binaries, they decided to use the same packer. Now, this is some very valuable knowledge. You have just connected not just 3 disparate malware families, but you know now that probably there is some connection between the actors behind these families, because somehow they all had the same packer. Now, we thought, okay, we're getting some really cool results. How do we go and verify? Okay, so we looked up, we found that, there are 2 malware families, Dark Comet and Optima, and they seem to be sharing some code. So we randomly picked a few procedures. Now, and we put them through BinDef. And we said, okay, BinDef, what do you think? Do they really match? And we look at the program, BinDef matches using program structure. So it draws up the graph and it looks at, is the structure the same? Well, it's the same. And now these procedures were not there in the original packed binaries that we had, but they were present in only the unpacked binaries. And as you can see, they were not there in all of the samples that we had. This procedure was there in 65 of the 319 Dark Comet samples that we had, and 13 of 159 Optima? Yeah, Optima bot family samples. So this shows a very strong connection. We also have a lot of other procedures, but again, another thing that we can do with this system is we can understand the evolution of a malware family. All the while now, we've been talking about connections between different families. But what if you have one family and you analyze just the code of that one family? And we go and we say, okay, in all of these samples from this one malware family, how many procedures are there shared across all of the binaries of that sample? And here is this graph. On the x-axis, we have the percentage of binaries in which the procedures were found. And on the y-axis, we have number of such procedures. So essentially, we had 200 procedures that were there in 100% of those binaries of this family, DDoSer family, and a few which were there only in maybe 10% of the family. Another thing that we can do is find needle in a haystack. So what happens when you have a malware family that is evolving very rapidly? Every few days there's a new sample and somehow the code has changed. Well, this system can tell you that, okay, the graph shows that on the left-hand side you have a lot of procedures, which means there are barely, only 20 procedures that are there in about 60 to 65% of the binaries. And most of the procedures are in less than 5% of the binaries, which means the code is evolving very rapidly. This is a new insight that we got into the malware family. And this is the intelligence brought by Virus Battle. So to summarize in a nutshell, Virus Battle is a system that has got several new key innovations to extract malware intelligence. We've got an unpacker that uses VM introspection. We have semantic fingerprinting. We also have min hashes, a form of locality-sensitive hashing for basically doing some probabilistic matches, so you don't have to go pairwise match every procedure to every other procedure in the sample. Instead, you can deterministically manipulate the probabilities according the probability function, and then say, with a very high probability, I should be able to match things that are similar, and the probability of a match for things that are not similar should be very low, and you can just do that by changing the configuration. And some of the results of performance, typically the unpacker, the generate automatic unpacker takes about 30 seconds. It spins off a VM and automatically unpacks the binary and saves you a whole new PE file in all under 30 seconds. And parallelly, we also are able to calculate the semantic hashes. So there's a separate process that goes on, and that also takes about 30 seconds. And you can query the system now because we have everything hashed and indexed. You can query on it and under, is it 1 second?
7 seconds.
7 seconds. Sorry, it's difficult to kind of read from it. And you can do is it what? Procedure search in under 100 milliseconds. And yeah, the system is very highly scalable. Each of these is a separate process, and like Dr. Lakhotia showed, VM introspection is also parallelizable, and so is Juice, and so are the queries. And we have a distributed architecture that is already explained. And so the things to take from this talk, basically malware repositories are a good source of intelligence. Until now, whenever the number of malware increased, people got worried. Oh, how do I save myself? The malware is increasing to such huge numbers. But if it's increasing to such huge numbers, it's also giving you a lot of information. You have now a much bigger source of information out there. And VM introspection essentially allows you to monitor the behaviors of a malware as it is executing in vivo live mode below a ring 0 level because you're monitoring it from the outside. Semantic Juice is able to peer through a lot of different types of code obfuscations like metamorphism, polymorphisms, and other similar obfuscations, which are typically considered very difficult to do. And semantic hashing enables a very fast search of code over various levels of granularity. Like we saw, we could search for similar procedures. We could search for similar code, basic blocks of code. We can even search for different binaries that are similar to the input binary. And finally, Virus Battle Malware Intelligence System is available to use online. It is also...
That's good. Go ahead.
Yeah. And it allows you to reduce your cost of reverse engineering. It allows you to identify targeted attacks. You're able to connect separate malware incidents, and so you know the attacks are connected. And it also provides for a faster incident response. Every time there is an incident, you can put the malware boundary in. You can find out some other similar malware that you have previously analyzed, and so you know how to respond to such incidents. Yep. I guess that's it. And questions?
Good.
Thank you. That was very interesting. One question. Do you know what is the reason you actually require semantic transformation? I mean, one assumption could be that the same source code is reused and different compilers are applied, different compiler options. Do you have any other theories why that step is actually required?
So I have a little hearing problem, so I got to have someone tell me what.
So
he
he's
can
asking
answer.
why you need semantic hashes.
Go
So basically, typically you also have obfuscations like.
Can you repeat the question for everyone?
So the question was that why do we really need to calculate bin juice semantics if it's just the same code that's being reused?
Okay, so that's a good question. So the same code is being reused. The code is reused, but remember, after taking the code, you transform the code. So the mechanism of defeating malware, antivirus, is applying certain transformation after the fact. So there are two types of transformation. You applied it on computer, actual binary itself, so you pack it. The packing is one transformation. But even with packing, what happens, there's some piece of code. And the way the code is hidden is by taking the same exact logic, but automatically by machine transforming it. So you remember I showed the pieces of code, say a sequence of code, and then I showed the variations that are essentially the same. That kind of transformation can be done by machine. And there are metamorphic, polymorphic, these transformation engines available that malware authors use, or rather there are software protection tools that are available that apply the transformation for you. So the reason we want to use the notion of juice is to deal with those transformations. In addition, you may take source code and then compile it. And when you compile, every time you recompile the code, there's a possible variation. There's some possibility of variations. You may also add new behavior in the code. So you have, it's not exactly identical, but there's some variations in the code. So the compiler, for example, may use different registers for the same logic. So you have the same code, but the compiler chooses different set of instructions, different registers, different memory locations. And so you want to remove those variations as well. Okay? Did I answer the question? Yeah.
Any other questions?
So if you guys want to try it out, we have a website, virusbattle.com. You go there, you're going to find the instructions to get the API key. Right now, as it's currently set, it's through a Python API package. So we give you some code, Python code, you set up your API key, and then you can hit our site. It's designed for people who want to analyze large collection of malware. So it's not a hobbyist mode right now where you can go to the browser website and upload things. It is for production sort of version where you want to do a lot of stuff and you don't have time to click around. Okay? So please send us, contact us. We're happy to provide you the access. Okay? Any other question?
No, there's one.
There's a question.
What kind of confidentiality for the submissions, where it came from? Do you keep that confidential, or is there any guarantee?
Okay, good question. So I'm assuming you're talking about confidentiality about information you upload on the service? Okay, so the web service currently is run by a university, and universities don't have as much confidentiality per se. As in, if you put the site, it's available online, and at this point we don't have any significant access control beyond the API key. However, this is a prototype system. It's for you to use to try it out on even large set, but it's not ready to actually connect it to a big fire hose and say, ooh, look, analyze 100,000 a day. However, given that, it's a good question, and I want to pitch. There's a little marketing pitch now. It's the end of the day, and I can probably excuse me for doing it. I am taking this as a professor. I'm taking this technology out of the university and creating a spin-off to be able to bring it to market so we can address the issues of providing SOAs and reliability and all that stuff, and deal with access control and works. Okay, so if you're interested, please contact me. Right? Question?
Yes, we're also out of time. We're out of time.
You're out of time?
Yeah.
Okay. I'm sure there's some party here today. Maybe we can go walk towards the next party and meet there. Okay?
Yeah. Thank you.